In this section, we're going to talk about power supplies and batteries and how we use them in our embedded systems designs. But really, why should we care about power? Well, my philosophy is that we should know about all the parts of a design. We should take a holistic view of our design so we can make our designs do as much as possible with as little as possible. This is efficiency of design. And a really well-designed system is going to be cheap, it's going to be simple, and it's going to get the job done better than a lot of other approaches, right? We would need to know our system limitations, such as runtime and what our and how long we can operate our devices if they're run off a battery, how much power they draw as we use them, if they're things that plug into the wall, stuff like that. We need to know what the limitations of our systems are. And we also want to minimize cost. We want to make sure that our systems work and our power supplies and our operations are done with as little cost as possible for production, for operation, things like that. If we know what the limitations of our power supplies are, we can sometimes write software that is more power efficient, which is a really strange concept, but we'll look at some of those approaches later on in the semester. Before we get into this, I want to review some basics of electronics, and the very most important piece of knowledge you need to know about electronics is Ohm's Law. This is the simplest and most elegant and most useful set of relationships in all of electronics. If I wanted to get a tattoo, this is what I would have tattooed on me. I would have the Ohm's Law circle and all of its relationships. And the most important part is the basic Ohm's Law relationship. This V is equal to I times R part here, right? Now let's review some basic concepts about these things. Voltage is the electrical potential energy, and you can kind of think of it as pressure. We're going to use a water analogy here, and in water we can have pressure, we can have flow, which is current, and the water itself represents charge. So here in this water analogy, charge is the little bits of water, just like the little bits of electrons that flow in a conductor. The pipe is our conductor, the water and the pressure that it's under is our voltage. It's the potential energy, it's the potential difference between things. And this is what we use to actually do work. Current is the flow of electrons in a conductor, right? So, and it's literally electrons hopping from one atom to another inside of a conductor. In our analogy, current is the flow of water, how much water is flowing. If I have higher pressure, then more water will flow through the pipe. Similarly, if I have a higher voltage, then more current, more electricity, or more charge will flow through a given conductor. And finally, resistance. Resistance is the opposition to the flow of current, right? And basically it's the resistance of a pipe. If I have a very small, narrow pipe, that's going to have more resistance to the flow of water. It's going to take more pressure to push the same amount of water through that pipe. Similarly, if I have a high resistant conductor, it's going to take more voltage, more pressure, more voltage to push the same current through that tiny conductor. We can also think of, when we're talking about power supplies, we can think of resistance as load, as kind of the what we're trying to power here, right? And the big relationship between these things is the best one. It's V equals IR. So V is equal to voltage is equal to current times resistance. And holding any one of these constant will cause the other ones to increase and decrease. So the relationship here is sort of holistic. We see all the pieces come together for the same pressure. If I have a higher resistance, if I have a higher pressure, if I have a higher resistance, then I should have the same current. That's what this one illustrates right here. The other relationship that we should know is power. P, power, is equal to voltage times current. And these are all three related, all four of these quantities are related values that are important to know. And really, if you memorize these, you can derive everything else. All of this stuff it sort of falls through all of these little relationships here. And what power really is energy transfer. It's measured in watts, which is joules per second, and it's related to the amount of energy being transferred through a system at a given instant. If we're talking about power or energy transfer over time, then that gets into total energy. It's not energy transfer them anymore as total energy of a system, and that can be called work or anything like that, right? So we've got a lot of concepts here, and what we really want to do is we're going to look at how power supplies work, what different kinds of power supplies there are. We're going to look at some of the characteristics of batteries and how they work, and what we need to know when we're designing systems using batteries. And we're going to finally look at power regulators and how they fit into the whole scheme, and really come up with a sort of holistic view of the basics of how power supplies interact with our embedded systems.